I1, I2, I3 is equal to capital Y, we are writing here, Y11, Y12, Y13, Y21, Y22, Y23, Y31, Y32 and Y33, V1, V2, V3, where Y11, the diagonal element, is Y120 plus Y12 plus Y130 plus Y13, and the diagonal element Y22 is Y210 plus Y12 plus Y230 plus Y23. Similarly, diagonal element Y33 is equal to Y310 plus Y13 plus Y320 plus Y23. This is what we get from the matrix that we had seen here. So, we are replacing this element by Y11, this element by capital Y12, this element by capital Y13. So, we can see that the other off diagonal elements Y12 is equal to Y21, and that is equal to minus small y12, that is the series admittance of the line between 1 and 2, it is negative of that, and y13 is equal to y31 is equal to minus y13, y23 is equal to y32 is equal to minus y23. Now, this matrix Y matrix of Y admittance elements is relating the current injection at the various bus bars to the voltages at the bus bars, and that is why this matrix Y matrix is called the bus admittance matrix. It relates the current injections at the bus bars to the voltages at the bus bars. Now, the elements of this Y bus matrix YII, that is the diagonal elements, is called the self admittance or the driving point admittance of the network at bus I, and the element Yij, that is the off diagonal element, is called the transfer admittance or the mutual admittance between bus I and j, and in short we can write this relationship as I bus is equal to Y bus into V bus. We can in the same way write this relationship also as V bus is equal to Z bus into I bus, where Z bus is the inverse of Y bus matrix, and Z bus matrix is called the bus impedance matrix. Now, we normally work with the bus admittance matrix and not with the bus impedance matrix. There are various reasons behind this. One of the reason is it is very easy to form the Y bus matrix by just inspecting the power network, whereas Z bus matrix is much more complex to form. The other aspect which is there is that Y bus matrix is generally sparse, whereas Z bus matrix is a full matrix. We will see these things. So, let us see what are the characteristics of this Y bus matrix. The dimension of this Y bus matrix is n into n, where n is the number of bus bars in the system. So, if you have a 3 bus bar system, as we had seen here, we had a 3 bus bar system. For this 3 bus bar system, we will get a 3 by 3 Y bus matrix. If we have a 10 bus bar system, we will get a 10 by 10 matrix. Normally, the power networks are very large, they are more than 1000 bus bars with many thousand lines connecting various bus bars, and therefore, we will be dealing with Y bus matrices which can be as large as 1000 into 1000 or even more. Another characteristics that we see for this Y bus matrix is that it is a symmetric matrix. That is, what we are seeing here is y12 is equal to y21 is equal to minus y12, that is minus small y12. So, what we are saying, y12 is equal to y21, y13 is equal to y31, y23 is equal to y32, that is, we are seeing that the matrix is a symmetric matrix. Another feature of this Y bus matrix is that Y bus matrix is a very sparse matrix. That is, almost 90 to 95% of the elements of the Y bus matrix are zeros, and very few elements which will be there are non-zeros. This comes mainly from the property that we have seen here. Now, if we see here in this network, there is no line which is connecting bus 1 to bus 4 and bus 1 to bus 5. So, the y14 and y15 are 0, and therefore, we will have no element, non-zero element for these in the Y bus matrix. Similarly, in a very large network, we do not have all the bus bars connected to all other bus bars. So, if we are talking about a 1000 bus system, then in that case each bus bar may be connected to some 5 or 7 bus bars. So, what we see is that there will be only 8 entries in that row for that bus bar, or in the column for that bus bar. So, rest of the other elements, 992 elements, will be zeros, and so will be the case with all the other bus bars also. So, we are finding that out of the 1000 elements, most of the rows and columns will be having only some 8-10 elements, and rest the elements will be zeros, and which shows that the number of zeros in the Y bus matrix will be very large, and therefore, these matrices are called sparse matrices, and we try to take advantage of the sparsity of this matrix in our computation process very much. In fact, sparsity is a property which is available or prevalent in all very large systems. So, Y bus is a sparse matrix. Diagonal elements of YII are obtained as algebraic sum of all elements incident to bus I. That is, we had seen that y11 or y12 is nothing but the algebraic sum of all the admittance which is connected to that bus. So, if you see here, y11 will be equal to y120 plus y12 plus y130 plus y13, all the admittances which are directly connected to this bus bar. So, this is how we can calculate or find out the diagonal element of the Y bus. Off diagonal elements Yij is equal to Yji, because the matrix is symmetric, are obtained as negative of the admittance connecting bus I and j.